Yes, and thank you very much, Stefan, for that brilliant introduction. So, my name is Anders Jarfors, and I'm professor at Jönköping University in materials and manufacturing with focus on casting. And I will be sort of the warm-up here today, and we'll talk a little bit about material quality and sustainability. Now, first of all, I will cover a little bit about the drivers and challenges for the aluminum industry, and then I will talk something about quality and rejection. And then there is, of course, something what it all boils down to, and you will probably figure that one out before the end. So now, the drivers and challenges. We have been seeing some rather fantastic news where things are changing for the aluminum industry. We know that in general, electrification is something that is driving a lot of change today. So we have green electricity, and for the foundry industry, that affects, for instance, resource efficiency when it comes to melting and recycling. The aluminum industry has been heavily influenced by the transportation industry, and electrification also drives a big change for the transportation industry and the powertrain redesign with the electrical drives. And then we also have the telecom industry that is growing, and it's huge volumes that goes to radio filters and heat sinks and such. One thing that everybody is agreeing on is that weight reduction is critical, and material change is one way of doing it. Another way is to cast better with less over-dimensioning and make things thinner and lighter in that. And if you look at the transportation industry, since a lot of the electricity still is produced with fossil fuels, it's essential that weight reduction is achieved in vehicles in order to reach the climate impact targets from the Paris Accord. So this is, especially during the transition, this is important. And then we have cost efficiency and circularity matters that comes into play. And everybody has seen the nice castings coming from Elon Musk and Tesla up to the right, and the big machine down to the right as well. And this also is a big change, because in the front and the rear of the car, you had 70 parts less. You have 7 parts less when you do everything as a single casting. And that means that you have 70 tools less, you have 70 joining operations less, and you have 70 procurement processes less. But also in terms of circularity, you do not have maybe 4 or 5 materials. You have only one material now, and that improves the circularity of the design as well, because there's only one material to take care of. So these things are important changes, and this is what drives a lot of the development and transition today. And if you look at the electrification of the industry, you can compare the efficiency of a number of furnaces, and all that are electrically driven, they all have lesser material loss during production. So if you have a crucible furnace, you have a relatively high loss. If you use induction, you have lesser loss. The same thing is you compare a reverberatory furnace to a gas-driven such with an electric furnace. It's a difference. And also the energy efficiency in the furnaces are increasing. So that means that the power requirements are reduced, the material losses are reduced if you use electrical power. And when we talk about material loss, you have a number of material that is being recirculated. And if you take a virgin material and then you have a certain amount going back into the melt as in-house returns, the embodied energy goes up. And that goes also the same for carbon dioxide emissions. So you need to melt more material, and you sort of accumulate environmental load in the material. And of course, it's better to use recycled material compared to virgin material. But the principle is the same. If you recycle material, depending on how much you recycle and depending on what type of furnace you do, you have different effects. And it's always better with electrical drives than with gas drives or gas-driven furnaces. So the thing that happens when you have greater material losses during your transfer, you have more slag to manage. It's not just the material loss, you have more material that can go into castings. And you can have cracks being formed, you have oxide layers, and they are also on the macroscopic scale. This is from a wheel, and all the mess here is essentially large oxide. And what you will see that if it fractures, oxide will go all the way through. So it affects all the quality of the part. And there is a number of ways we try to characterize this. And this is something that Murat will cover a little bit more about later. But there is a difficulty in understanding what is a good melt and what is a bad melt. But we know that during the melting process, if you have a lot of material loss, you generate more slag and there's a higher risk for it to enter the system. Now, these are data that was presented during the S2P conference in Austria, where we talk about semi-solid casting. But that is not the focus here today. But the important part here is that if you compare the shot weight with the part weight, that means that you have a certain amount that is gating systems, and then you have your rejection rates, and that gives you a certain amount of material that is being returned. And this increases the oxide content of the material because you have gating systems, you have vent lines and things like that that goes back into the melt. And you have material losses and you have accumulation of energy and carbon dioxide that will sort of drive the climate impact of your foundry. So these are numbers that you would find in from foundries. And if we take a serious look at this, of course you have certain amounts of embodied energies per kilo and per part. And the interesting portion here, if you look at the embodied energy per kilo, it actually goes up if you have a part reduction and do not change your gating system. But the embodied energy per part goes down. And it's the same thing with the carbon dioxide footprint. So it's also important on how we measure and understand what we actually do in the processes. But the essence here is still, if you look at the industry, we all know that rejection rates boils down to the last line on your economy. So it goes directly down to rejections, but nobody really cares about the return rate. Of course, it's important not to have a high return rate, but when it comes to the contribution from rejections or gating systems, the rejections in a foundry are essentially a minority in when you have an efficient process. So that means that if you look at the competitiveness of a company, rejects are of course important, but when it comes to the carbon footprint, gating systems are critical. And this is something that has not been properly addressed yet. And if we think about the gating system, that means you need to have a good fluidity in order to be able to reduce those. And that means that you need to have control of your melt. And that is essentially what it all boils down to. If you do not control your melt, that means you need to have a high resource efficiency. That means low losses during melting, short melting times, and generate as little as possible of material loss and slag that can damage the material further downstream. So if we try to conclude this in some way, the lightweighting application, that means it's seldom so that the load of a component is being reduced, but the requirements on the material is increasing. And there's also a change when you look at the applications of the castings. There are new applications where you have crash safety and other critical demands. And that means that we need to manage both porosity and damage in the materials. So that means ductility and fatigue performance needs to be increased. And if you look at the increased performance on foundries, this is essentially also the sustainability requirements. It's not only profitability, you also need to reduce your emissions and your carbon dioxide footprint. Electrification is critical, and if you reduce your returns in the foundry, that means that you will have a lesser amount of energy per product being used. And since the runner and gating dominates this and the climate impact, this is something that we need to work with. So the solution to all these issues is to minimize gating and reduce rejects by having control of your melt. And that means manage your damage. I would like to send my thanks to my colleagues at the Jönköping University and my colleagues in the chat. Sorry, there is a recording here that comes in. Sorry. So for some reason this, well, I'm supposed to end here and I should hand over the presentation to Madeleine. So it was something that ended with the previous presentation. So I'll stop sharing here and hand over to Madeleine.
Thank you very much, Anders, for this final presentation. And it was a bit funny. Everything can happen when you have these webinars. Yes. So thank you very much. And now it's time for our special guest, Murat. Please join us with your camera and your presentation. And I leave the floor to you.
Well, hello everyone. Thank you for joining us. I would like to thank Madeleine and Stefan for organizing this and Anders for inviting me to join this wonderful webinar series. I am joining Jönköping University at this point on a one-month loan from Jacksonville University. And I was asked to talk about quality, but I said, let's talk about damage and where it comes from and what it does, what the current thinking is in the aluminum metallurgy at this point. What is the current technology? How do we produce the castings? And once we understand where the damage comes from, we may have a second critical view at the technology. So once we understand the source of damage, how do we quantify it? What are the tools and metrics that are available to us that is easy to use? How can we quantify the filling system damage so that maybe we can improve the filling system and perhaps make it small, have increased sustainability? Then how do we quantify the overall damage? And basically, I'm going to leave with some food for thought at the end. So let's get right into it. What is the current thinking in our aluminum foundry industry? What do we think we know? First of all, there's a general consensus that the pores are by far the most serious defects in aluminum castings. But if there are no pores, life is good. And pores are mostly unavoidable. So the best we can do is to minimize pores. And one of the #1 enemies is hydrogen. Get hydrogen out of there. Then there are important microstructural parameters to control only in aluminum castings, not in wrought alloys, but just in aluminum castings. The dendrite arm spacing comes to mind. Silicon phase in aluminum silicon alloys because silicon is so brittle, and intermetallics like iron containing intermetallics, which brittle, make the castings very brittle. Ductility is inherently low, much lower than in wrought alloys, although it's the same metal. And it's difficult to make money in castings. So there's an alternative thought to this, and it's been developed by my good friend, PhD thesis advisor, Professor John Campbell from University of Birmingham, who tells us that there are 10 rules to have a good casting. And I'm going to cover basically 3 of these today, starting with good metal, no surface turbulence, and no entrained bubbles. I've also had the absolute privilege to work with one of the leaders on the roadside, Dr. Jim Staley, who was chief metallurgist at Alcoa for a number of years, who taught me that most of the things we see in aluminum are extrinsic. That means they are not supposed to be there, but they are there because something went wrong. But there is also intrinsic. So what's intrinsic, what's extrinsic? And he said, well, hydrogen is extrinsic, ores are extrinsic, inclusions such as oxides are extrinsic. So my thinking was heavily influenced by his expertise and his advice. All right, what is the damage and where does it come from? It comes from entrainment. And what is entrainment? Basically, let's look at this wonderful picture from Jacksonville Beach that I took about a month ago during one of my walks on the beach. We look at the beautiful ocean, and what we see is a lot of water. And of course, the surface of water is covered by water. And that is the liquid that everybody is completely familiar with. Our lives depend on it, and our approach to liquid metal is also deeply influenced by our familiarity with water. The surface of the liquid aluminum, however, is not covered by liquid aluminum. It's covered by a solid ceramic, and most of the time it's alumina. And when we treat liquid aluminum, just like we treat water, that's where the problems start. Because as long as the surface oxide remains on the surface, we don't have any problems. It's a protective layer, it's good, no worries. But when it gets entrained, because we disrupt the surface of liquid aluminum, that's where the problems start. And then this ceramic gets folded on itself, and those two films form that touch each other, and there is no bonding between. There's some air and entrained as well. So the result is what you see schematically on the left. So we have an entrainment defect, and it's called bifilm because there are two films touching each other. And there are air bubbles. Most of the time they leave behind oxide trails because the air inside has oxygen, so it reacts immediately with the aluminum, and then with nitrogen it leaves trails of ceramic. So when we disrupt the surface of water, let's say we throw in ice cubes, and it would be similar to putting in reject material or the gating system into the liquid melt. You'll see that it leaves trails of air, and in the case of liquid aluminum, it would be air plus the trail of oxides that goes in. So the disruption of the surface is not a good thing. In the end, we have these bifilms entrained into the structure. Here we see a highly tangled bifilm. We can even see one of the layers that shine through. But there are many, many examples of this. I'm going to show a few. These are coarse old oxides that come from the crucible that the surface layer has been transported into the main body of the casting. And when you look at it under the optical microscope of a tensile specimen, this is what you see, black areas that these are coarse oxides. Now, obviously, this is not just pure aluminum or aluminum alloy. It has a lot of alumina in it because of the surface entrainment. And there are young bifilms that are only maybe nanometers thick. They form in a very short period of time, perhaps when the air bubble is rising or when you're pouring the metal, as we usually do. These form instantaneously, and they get entrained into the body of the casting. Then we see bubble trails. You see on the left-hand side in a zinc casting, die casting, a bubble trail. You see the bubble at the top, but you see the trail at the bottom. On the right-hand side, you see the trail that looks like an old dry tree. Those are the oxides left behind by the bubble that get moved up by buoyancy. And when you come across something like this, it is basically bubble trails, but you look at it from a different angle. You're looking at it from bottom up. So these air bubbles are highly damaging to the liquid aluminum, and later obviously to the casting. So let's take a look at how we produce castings. And I found just one video, and I'm going to share that with you so that we're all talking about the same thing. We're on the same page. This is a YouTube video. So I'll jump right to the point where, so we have the primary furnace where all aluminum is melted. It gets poured into this transfer ladle, and it's transported by the forklift to the machine where there will be the main, and you can see that, please notice the air bubbles, the violent surface phenomena that's going on in the crucible, on the lower crucible. So it gets poured from several meters. There's a lot of air that gets entrained, and obviously I don't need to tell you that this is a perfect way to damage the liquid metal. And look at the surface of this. Surface gets entrained, air gets entrained, and that's how we do it. So how do we treat our liquid aluminum? With what I call bucket technology, because we're so used to water. We keep on treating liquid aluminum as if it's water, and we don't see anything wrong with that. But there's a lot of things that's wrong with that. And what you have seen is that we don't have only one bucket, we have multiple buckets. So we pour from one bucket to the other. And the damage that happens in the process is significant. So let's talk about the damage of the melt transfers. In civil engineering literature, it's called plunging jets, and it's known as an excellent way to create a liquid air mixture. Here you see water on the left-hand side, it's full of air, and as long as it's water, there's no problem with it. But when it's aluminum or any other liquid metal, that creates a huge problem. I have another video, and it's again from YouTube. On the left-hand side, upper left-hand side, you see the liquid, the water coming in to the surface of water. On the lower left-hand side, you're going to see what goes on beneath the surface. And on the right-hand side, you'll see a magnified version of that. So everything you see is air being entrained. You don't see the water coming in. Everything you see is air. So when we do these melt transfers, we are entraining, and you can see the bubbles rising on the right-hand side. So when we have these melt transfers, all we do is create a liquid aluminum air mixture. And here's another research that I came across, again from air liquid aluminum mixture created by pouring from one bucket to the other. Here at the beginning, we have 65% air, only 35% liquid aluminum. And with time, it goes up to about 18%, but that's still a lot of air, a lot of damage that's created just because we treat liquid aluminum as if it were water. And then we have what is supposed to be cleaning. I'll talk a little bit about that later on. But cleaning means, okay, we damaged the metal a little bit, so let's put some flux in there. We know that hydrogen is bad, let's get it out of there. And what do? We do rotary degassing. So rotary degassing unit is immersed into the melt, obviously disrupting the surface significantly again. And then you're going to see a huge vortex that happens, and all of the surface gets entrained again. But in the meantime, argon is pumped. Argon is known to take the hydrogen out of there, and we end up with metal with low hydrogen content, and which is supposed to be clean. And we will talk about that later on. So what we do in this process is basically we use the broom technology. And what do we do with the broom? We take the dirt and we put it under the rug so we don't see it. If I don't see the dirt, if I don't see the damage, then it doesn't exist. And I wish life were that simple, because they come back to haunt us. Then there's damage during mold filling. I have an example, a couple of examples, basically from a sand casting process. One is this classical video from early 90s from the real-time X-ray at the University of Birmingham. So I'm going to play this video. You're going to see that the mold is going to fill very quickly, but because the gating system is not full, you're going to see some air bubbles that go through, and we're going to watch a slower version. This is the slow version. There's a huge hydraulic jump. Air is entrained because we have the wrong gating or filling system, and that air, of course, has buoyancy that goes up, leaves all kinds of oxides. Some of that is left behind. But if you were using the right gating system, then air entrainment would not happen. The surface of the liquid would be kept uniform, and there would be no entrainment, no additional damage, I should say, during mold filling. But if we did all the melt transfers before, this part really doesn't matter. The damage has been done, because damage is cumulative. It starts with the ingots, it starts with the melt preparation, it goes on. Every time we disrupt the surface of the liquid aluminum, damage is introduced and it becomes added. All right, so let's go to the next one. Here we have the plexiglass version of the filling system by one of the foundries, and they wanted to see, they want to observe what happens in the casting and how the gating system is performing by having a watermark. And this video is about that, and I'll just play the video. And this is supposed to be the mold cavity. The type of the mold cavity doesn't matter. We have the gating system. These are the gates that you see in there, and they have not turned on the water yet. And once they turn on, you'll see what happens. And you see basically an air water mixture coming in. And you'll see that a lot of air is being entrained in the sprue, and that goes right through. And you have air, air, air. Perfect way to damage the casting. Irreversible. Okay, I think you got the idea. So when we come back, I want to pour some, at least my wisdom on what the current thinking is. Everything that we see here, whether pores, microstructural parameters, ductility, or return on investment, how much money we make. That's all due to damage. It's controlled by damage. And if you want to make more money, you have to control your damage. If you want to get more quality out of your production system, you have to understand where damage comes from, and you have to control and manage it. So what are the tools and metrics we have available at our disposal? I'm going to recommend two, and they are well known to all foundrymen, the tensile test, because no entrainment damage can hide from this test. No entrainment damage can hide from a tensile stress. Then the reduced pressure test, but with a caveat. The caveat is that we have to have enough hydrogen in the melt so that we can see the damage. Removing the damage or removing the hydrogen hides the damage. And I will talk about that as well. So let's jump into the tensile test. Conventionally, we look at 3 points on the curve. The first one is the yield strength. The second one is the tensile stress. And the third one is elongation. Among the three, yield stress is minimally affected by defects. Tensile stress is slightly affected by defects, and elongation is significantly affected by defects. So which one are we going to use, and how is this going to look like? So before I give you the answer, let me talk about what we can actually get from the metal. So I looked at about 10 years ago, I looked at the premium casting and aerospace casting literature. So I put in all the data that I could find on several alloys. This is for aluminum, silicon, magnesium alloys. We have about 323 data points here. And what became obvious is that the maximum points form a trend. When you plot yield stress on the x-axis and elongation on the y-axis. So that seems to be the intrinsic ductility strength relationship compromised, as we learned in the textbooks. So we call that the potential, the ductility potential of the alloy. So you will see that, for example, at 200 megapascals, we are capable of getting about 24% elongation from the casting. Again, these are actual numbers. These are not estimates or theoretical values. These are actual numbers. So the best fit to this maximum line or ductility potential line for aluminum, silicon, magnesium alloys is 36 minus 0.064 times yield stress. Okay, how can we use that? I propose that we have a quality index. So when we run a tensile test and have our data points, basically we need the yield stress and the elongation. And then based on the yield stress, we calculate the ductility potential. And basically the quality index is the elongation that we get from the tensile test divided by the ductility potential that would come from that simple equation. So we can get an idea of how much we're getting from the metal. So when we look at the the yield stress versus elongation area, I divided into 4. Anything below 0.25 is highly damaged. Between 0.25 and 50, 0.5 is moderate damage. Between 0.5 and 0.7, maybe 0.75, is low damage. And above 0.7 and around 1, that's very good, but that's very low damage. Now, I have not found any data yet above this 1.0. I expect that as we improve the technology, we can get there, and we can improve. We can get a new equation for the ductility potential equation. Okay. So reduced pressure test is the second one. As you know, we collect a sample, we put it in the chamber, we turn it on, there's a vacuum, the vacuum opens up the pores. And what we see here is classical work from 20 years ago. You see under atmospheric pressure, this sample, you're going to notice some gray areas in the middle. And when the pressure is reduced, the air entrained within the biofilms increases in volume. And as a result, we can see the real damage. And when you look at that, you can see the crack-like nature of the oxides, of the biofilms that get entrained because of the damage that has been given to the metal. Okay, so what are the important concepts about damage? I will come back to these several times. First of all, pores are only the visible parts of overall damage, meaning the real damage is much more extensive. Closing the pores with maybe secondary processes or some other techniques is a very low return on investment. My advice is don't do it. Money spent in the wrong way. And I'm going to give you a couple of examples. First example is squeeze casting, where we apply pressure during the solidification process so that the pores don't open up. Here's some data I found from the literature. It's an LM24 alloy, I think 8% silicon and 3% copper. So when we look at the numbers, yield strength about 120, 126. When it's T6 condition, heat treated, it goes up to 330. Quite a good response to heat treatment. When we look at the elongation numbers, we see 2%, 2.72. What's wrong with that? We're used to 1%. 2% is not bad. Okay, let's put that into perspective. The maximum, the ductility potential of the alloy at that yield strength is 29, 28, and 15% respectively. And when we calculate the quality index, it goes from 7 to 10. So when we apply 100 megapascal of pressure, we go from 7% quality index to 10%, an increase of 3%. And then when we heat treat it, there is some beneficial effect of solution treatment in healing the oxides, but very little. You gain another 3%. So what do we learn from this? Yeah, we have a lot of expensive equipment applying the pressure. Basically, the quality index remains unchanged, and we still lose about 90%. 90% of available ductility to damage. And that has tremendous implications for the performance of the casting, especially fatigue performance. And that may be another webinar in the future. Okay, how about another process, hot isostatic pressing, where the metal is heated to about 500 degrees and we apply some pressure on it. Here's what I could find from the literature. When you look at this, okay, there seems to be some improvement between hipped and unhipped, but when we pay close attention to the y-axis, the scale, we notice that it's really, really zoomed in. And if we zoom out, as I do, on the right-hand side, you're going to see the data points all the way at the bottom, which basically overlap. And I give you the ductility potential, which is about 22% at that yield strength of 225 megapascal. And the quality index that we end up with is 2 to 2.5%. 2% of what we can get from the metal. What does that mean? Applying pressure after solidification closes pores. There are no pores left, just like in the previous one. We don't see the pores anymore, it's gone. But the damage has been done, the damage remains. As a result, we lose 98% of what the metal is capable of giving us. 98% is gone. 98% is gone. All right, I want to give a little bit more insight. Why do I say pores are only the visible part of damage? We conducted this study several years ago. We poured metal from different heights, and obviously the higher the pouring height, the higher the damage. We can all, but we quantified it. It's all in the paper. I'm not going to spend much time on the paper, but we noticed something when we were looking at the mostly damaged specimen. This is the RPT specimen. We cut it into half, and we looked at it. Okay, you can see the huge pore expanded to, we thought, maximum limit. It cannot expand anymore. Then we saw this curious feature that you notice with the arrow. What is that curious feature? And we zoomed in, okay, and then we did X-ray mapping, and it's oxygen. So that means there's a folded oxide there. There's a biofilm that's hiding there, and it couldn't open up. So the huge pore that we saw was only a part of the damage. And we started looking somewhere else. Okay, we looked at this. All right, there doesn't seem to be anything curious about this feature. Turn the X-ray mapping, and there you see the hiding biofilms shown with the arrows. More biofilms are hiding because the air in there that we expanded, we thought, to the maximum, was not sufficient to open up all the biofilms. So the huge pore that we looked at was only a part of the damage. There's more damage in there that just did not open up. I came across this in fatigue literature, something they call fissure. Here's a pore. There is what they call fissure, and when you read fatigue literature on aluminum castings, they say, oh, the cracks start on the first cycle. It's not a fatigue crack, it's the damage, it's the biofilm that's opening up. And simply because pores are surrounded by biofilms that have not opened up. The damage is much more extensive. So if we were to remove the oxygen, then we would remove these pores and we would basically hide them. What the damage cannot hide from is a tensile stress. So these inactive oxides open up in tension. Here's a picture from an in situ tensile test. You see a pore and you see all these cracks around it opening up just at very low stress levels. Why do they open up? Because that's the damage, that's the inactive oxide that did not open due to any kind of feeding problem, any kind of negative pressure that occurs, contraction that occurs during solidification, or gas that goes there. And there's one more example, what's known as crack. That's basically more of the same, the hidden damage opening up in a tensile test in a tensile stress state. And this is a study by some of my colleagues here at Jönköping, in situ fatigue test. What they noticed is that there were these cracks that appeared in the most unexpected places, on the tensile side. These cracks, which are not fatigue cracks, these are just biofilms opening up. This is the damage presenting itself in a tensile stress state. So if we come back to the second concept of the damage, we talked about the pores. I'll go against what many of you have learned. Hydrogen is not a contaminant. Hydrogen cannot form pores without entrainment damage. That has been proven. Hydrogen makes the damage visible. So when we degas, we hide the damage. Basically what we do is sweep the dirt under the rug. And if we approach it from a systematic and strategic point of view, hydrogen can be our friend. And why do I say that? First of all, the solubility of hydrogen in liquid aluminum is an order of magnitude lower than in solid iron. So we're not talking about huge levels of hydrogen. Aluminum does not like hydrogen that much. Not much is soluble. But people say it's not really the solubility level, it's the difference between solubility. This gap, it goes down quite a bit from the liquid state to the solid state. And there's some truth to that. When we calculate, and we have this weird unit, milliliters per 100 grams of aluminum, I converted that to atomic ppm for your information. So for 1 million aluminum atoms, we're talking about 22 hydrogen atoms, and in liquid, and 1 in solid. And again, but we're talking about pure aluminum. So when we look at this, what I call the supersaturation, so if we immediately go from liquid to solid, that's about 22. So what does that mean? 22. So that drop is 22. Okay, so I divide liquid solubility by solid solubility. But this is for pure aluminum. But what happens when we have commercial alloys? And this paper of mine came out earlier this year, in which I calculated. These are estimates, but I think they're pretty close. For 206 aluminum 5% copper, right? It behaves just like pure aluminum. So I divide the solubility at liquidus by solubility at solidus, 21.7. When it comes to aluminum silicon alloys like 319, 8356, well, we have a much better or much smaller problem. About 3 is what we're talking about. So that gap that we've all learned about is not that big. And when it comes to these die casting alloys, I found something that I never thought I would see, and unexpected. It's lower than 1. What does that mean? The solid alloy can dissolve more hydrogen than the liquid alloy. So why do we need to worry about hydrogen in these alloys? We don't. Okay, let's keep on talking. There's this. I came across this one wonderful study by Professor Gruzleski from Canada, in which he dipped a crucible with a filter at the bottom, And then they counted the number of inclusions they caught in the filter. And then they looked at, that gave an indication of what the damage was in the unfiltered melt. And then they looked at, okay, what's the effect of hydrogen level and what's the effect of the damage level? So I reinterpreted their results, but this is what they could catch in the filter: oxides, inclusions, all of that, all the dirt we have in the metal. Oh, by the way, these filters are about 50% efficient, 50 to 70%. So they did not catch all the damage, but they caught maybe half to 70% of it. So they had these reduced pressure tests, what they called clean, less clean, and dirty. I say moderately damaged, highly damaged, and extremely damaged. And different hydrogen levels. They are high hydrogen levels, but different hydrogen levels nonetheless. These are the RPT samples. We can see the difference, what the damage makes, and also what hydrogen makes. So the lower the hydrogen, the less the pores, but we increase the damage, the pores increase. So I took their data and I took a second look at it. Here on the x-axis, you see the number of inclusions that they caught. So that's a measure of the damage given to the metal. On the y-axis, you see the volume percentage of pores that they catch on the RPT specimens. And different curves are for different hydrogen contents. And when we plot them, basically, okay, the higher the hydrogen, the higher the pore volume. Okay, that makes sense. But the sensitivity to inclusions increases with increased hydrogen content. Okay, makes sense as well. All curves start at 0, 0. All curves start at 0, 0. Okay. So if there's no damage, that means the hydrogen content would not matter. So that's basically what I could learn from this. And if we were to do degassing and bring the hydrogen really low, what would we expect? We would expect this. Oh, degassed melt. There is not much to see. Okay, let's move on. Melt is good. But degassing is a perfect way to hide the real damage. And then this is this wonderful study from 1964 from Alcoa. They worked with an aluminum 4.5% copper alloy, 2014. They had two different levels of vacuum. I'm looking at the lowest vacuum. This is very, very low, about 0.6% of 1 atmosphere. And they looked at the effect of filtering, deep bed filtering. And obviously, when you filter, you get much less pore volume, and that makes sense. But there are a couple points that I want to draw your attention to. First of all, let's look at this point, which is filtered, but it's lying on the x-axis, which means it has 0% porosity. And let's compare it with, when we're going to compare it with another point, but just to give you an idea, at this vacuum level, the supersaturation is 147, meaning that the sample, the specimen, had 147 times the hydrogen solubility, the maximum hydrogen solid could dissolve, and still no pores formed. 147 times, not 147%, 147 times what the solid could dissolve, and still no pores. If you compare it with this one, same hydrogen level, you get about 22% porosity when it's unfiltered, when it's damaged. So that is the effect of filtering. That's the effect of getting the oxide films that come with the skin of the ingot, the skin of the rejects, the skin of the gating system that you put in to the melt. All the damage caused by the rotary degas, when you get it out, that's what happens. Well, that's not all. There is one more point, and it's this one. It's again lying on the x-axis. And when I did the math, the supersaturation is 332. The metal had 332 times the hydrogen it was supposed to hold in equilibrium, and still no pores formed. There cannot be any more convincing evidence than this, that hydrogen by itself is not damaging. So how do we quantify the damage? We have to try to learn how much damage we give to the metal at every step. First of all, what is the incoming damage? How much damage are you paying for when you buy ingots? Then the work in process damage that we cause during production. How much damage are we causing in the melt transfer when we add secondary aluminum rejects? And what I call cleaning efforts, I'm not sure that it's cleaning, such as flux, degassing, etc. Filling system damage, and then finally the outgoing damage. So I'm proposing that you have a dashboard of how much damage you have. So for the incoming damage, you can cut a sample from the ingot, machine the sample and melt it, and put it in the RPT mold and cut it in half, grind and polish, and then the number density of pores will tell you how much damage there is. So we have a case study here. We have the direct chill ingot and gravity die. Not all ingots are the same. We have much more damage from the gravity die. These are some of the metrics you can use: total pore area, pore volume fraction, biofilm index developed by my good friend Derya Dushplar, who I think is in the audience today. Or you can do a tensile test. You can excise a tensile specimen. Here from the same ingots, we have 1% from the gravity die, and we have about 24 or 10.9% from the direct chill casting. When we look at the quality index, one has 0.04, the other one has 0.4, which means it's 10 times better. Then how much damage do we have in the work in process? Important concept, again, rotary degassing actually damages the melt. Flux makes the melt mediocre. We learned from Dushpnar and his co-workers that fluxes are about 50% efficient. When you have a bad melt, it makes it mediocre. When you have a good melt, it damages it to mediocre level. So at every stage in the process sequence, so you have the big furnace, take a sample, take an RPT sample, take a tensile sample. After the melt transfer, take a sample, RPT sample, tensile sample. Second melt transfer, again, before, after, and all of these. You don't need to do it all the time, but you need to do it every now and then. And it's not very expensive. It's not, it does not interrupt the production, but you need to get data. You need to understand how much damage you're giving to the metal. How do we quantify the gating system damage? We had a case study, a casting here. We had 3 tries with it. It's a real casting. We tested the effect of the pouring basin, and then whether the vortex worked or not. In the 2 first ones, we used the flux. In the third one, we did not. We've used a direct chill ingot. You'll see that the gating system is very slim, designed based on the concepts developed by Professor Campbell. So there's very little air entrainment during the process. So we cut the sprue, polished it. So this is, instead of throwing the gating system into the melt again, you can take a small specimen, polish it, and look how much damage is you can see. You can see the damaging effect of flux on the left-hand side. On the right-hand side, there's not much. So that's the effect of flux, makes it mediocre again. These are the risers, feeders that we have sliced in the middle. We take a look, but it's the same story. So we could look at the sprue feeder. When we look at this, the pouring basin depth had no effect. That gave us a good information. When we look at this, flux had a very detrimental effect on the quality of the casting. And overall, you can see that the beneficial effect of the vortex gate. So there's a lot that you can gain by looking at what you already have. When we produce inclusions, we produce biofilms like sand, or even when we add grain refiner. All that grain refiner does, it distributes porosity. Here's an RPT of a grain refiner, courtesy of Derya Dushmana, and what it does is just create pore. So grain refiners, the real purpose is porosity management. There's no need to add grain refiner modifier when the melt is clean. That's what they practice in aerospace castings. You don't need it. Just do not disturb the surface of the liquid metal. So I'm coming toward the end. How do we quantify the overall damage? Just attach, have a little extra area in your casting. It's common practice in aerospace. There's a coupon attached to the casting. You cut it off and you excise a specimen and you run a tensile test. You don't need to chill it. It needs to solidify under the same conditions. It gives excellent information about the quality, the outgoing quality of your production system. So that we can perhaps in the end, when we collect all this data, we can develop what I call an operating system of the operating curve of the production system. And what do I mean by that? I'm going to give you 3 examples. One was reported by Professor Campbell. He reported these results came from a foundry where they looked at the results. No matter what they did, the quality index fluctuated between about 5% to 30%. And there was a lot of scatter, but even the best efforts produced about 0.25. And so they were operating on a curve. So they went from one side of the curve to the other. So in the end, the founder decided to revise their production system. Second case comes from a research laboratory in Canada, this 319 alloy. I took their data, plotted them, low hydrogen, high hydrogen, doesn't matter, it falls on the same curve. Here I plotted the pore volume percent versus quality index. What I did here is I zoomed in. Let's zoom out. When I zoom out, what do we see? This is the operating curve of the production system. So when we degas, all we do is we move on this curve. We go from left to right or right to left. But the main message is that even when we do our best, meaning the y-intercept, there's the inherent damage in castings due to production system. And in this case, we're losing about 77% of the potential of aluminum based on the entrainment damage. Okay, this comes from a real aluminum casting production facility. We published this several years ago. I think my co-worker Gassem is also in the audience. And we reported, okay, how can we optimize the degassing procedure? Okay, sometimes degassing can damage, and we can actually see it. Some of the times we can't because hydrogen is gone. But when we plot the data along with tensile tests, this is what we saw. Okay, the number of pores on this RPT specimens versus the tensile tests. When we zoom out, this is the operating curve of the system. And again, it's the same story. We lose about 70% due to the inherent damage in the production system. So I want to end my presentation with some words of wisdom with one of the most recognized quality experts, Dr. Edwards Deming. He said, defects are not free. Somebody makes them and gets paid for making them. I revised it slightly. Damage is not free. Somebody makes it and gets paid for introducing it into our castings. So in conclusion, most, if not all, our issues that we deal with can be attributed to the damage given to the liquid metal just because we treat it like water. We have to start seeing the damage, where it comes from, and then when you start seeing it, you cannot unsee it. Then you cringe when you see it. Then we can start quantifying the damage, incoming, work in process, filling system, outgoing damage, the damage given to the liquid metal that the customer is not paying for. The customer wants good product from us, but maybe they don't. And so if there are users of castings in the audience, why is it okay to get 1% from the casting that you purchase? Let's determine the operating curve for your production system. Reduced pressure test, metallography, and definitely a tensile test. No damage can hide from a tensile test. Then start the improvement journey. What is your loss, entire loss due to damage? Hydrogen is your friend, not the enemy. Makes the damage invisible. Stop sweeping the dirt under the rug. And it's possible to get no pores with high hydrogen content, high elongation, and make good profits. And thank you for attending. Tack så mycket in Swedish.
Thank you very much, Murat, for this presentation. And now I hope you are curious and want to join in the panel discussion, all of you. And I guess you will take care of that, Anders. So I leave the floor to you again.
Yes. So thank you very much, Murat, and thank you very much, Madeleine and Stefan. I must say, I really, really enjoyed your last comment there, Murat, when you said that well, defects or damage is not free, that you actually pay somebody to make them. I think that was spot on. Maybe we can look if there is anything from the chat, and maybe I can ask Madeleine and Stefan to help us a little bit on that when it comes to questions.
Actually, the chat is empty from questions for the moment, but please do add your questions.
Okay, so then Murat, we have some thoughts that we would like to discuss, and we also would like to maybe share some questions with the audience as well. So first of all, what are the causes and return in your production? So thinking about that, when you have your system, why do you get return material? That's your first question. Is it because of damage? Is it because of gating systems?